And it's Naka. Determining polarity. Take one.
Thank you, Mecca. Okay, so far what we've looked at is what type of substances we've got, so molecular, covalent networks, metallic and ionic. Here we're just going to be looking at molecular substances. And with molecular substances, we've already looked at how we can do a Lewis diagram and a three-dimensional diagram to show the shape of that. So that information is really important for determining whether something is polar or not. And I'm going to give you a bit of an overview, very quick overview on how we can use that knowledge we've already got to say straight away it's polar or it's non-polar. The importance of that comes later, insofar as what it will dissolve in or what it will dissolve. And one of the easiest little phrases to remember when you do that is like dissolves like. So a polar solvent will only dissolve polar solutes well. And a non-polar solvent, like petrol for example, will dissolve non-polar solutes like iodine, for example, very well. But it won't dissolve things like salt is a good one. Okay, so the first thing I always look at when I do my Lewis structure and then do my three-dimensional diagram is I look at the central atom. This is always looking at the central atom because that's where the dipole gets created around. And I go, does it have a lone pair of electrons? If the answer to that is yes, it means that it has an asymmetrical electron distribution. Okay, so it has asymmetry of charge. That's a nice phrase to use in your exams as well, asymmetry of charge. So if that's the case, if the charge isn't distributed evenly, it must be polar. So if it does have a lone pair of electrons, we can know straight away that it's polar. Now if it has, when you get to level 3, this doesn't always work because sometimes lone pairs cancel out, recreating symmetry. But for level 2, this is a nice easy way to say it, to look. But it's not a good enough answer in your exam. You need to say that it has an asymmetrical shape or an asymmetrical distribution of charge, or charge distribution. Okay. So the reason is not the lone pair of electrons, because that would be wrong next year, so we're not going to say that it's right this year. The reason is the asymmetry of shape, and so therefore the asymmetry of charge distribution. That creates a slight dipole. Okay. But if it doesn't have a lone pair, you've got to look at something else. And so what we look at next is whether it's got polar bonds or not. Okay, so we use that electronegativity difference to determine, are there polar bonds around the central atom? So I'm just going to say, does it, to make it easier, have polar bonds? And remember, electronegativity difference, and if you don't know the electronegativity values, be aware that the top right-hand corner of the periodic table are the most electronegative elements, so they usually have polar bonds. The rest of them normally don't, for the things that you're working with. Okay, unless of course it's ionic, and then it's the other extreme of the continuum. Alright, so again we've got two options, yes or no. If the answer is no, it doesn't have polar bonds, then there's no way for there to be a permanent dipole. There's no lone pairs of electrons, there's no polar bonds inside the molecule. It can't be polar. So therefore we get the answer straight away. It must be non-polar. And an example of this is something like methane, CH4. That's a good example of that. It has a symmetrical shape. It has symmetrical charge distribution because none of the bonds are polar. Okay, so that's a really good example there. Sorry, I forgot one over here for the polar one. A really good example is water. Okay, so H2O, because its Lewis structure shows those two lone pairs of electrons, and its three-dimensional structure shows that bent shape, which is not symmetrical. Okay, I know it looks symmetrical through there, but it's not, because the electrons have to be considered in that. Okay, so sorry, go back to that one. Okay, so what if we don't have a lone pair of electrons, but we do have polar bonds? Surely that means it's polar. Well, no, not always. So there's a bit of a curveball here. We need to find out if these polar bonds cancel each other out, so if they go in the opposite direction to each other. So I'm going to say, do the dipoles cancel out? Now, if you need me to explain it to you later, let me know. But a polar bond creates a dipole. And I'll show you what I mean by them cancelling out in a moment. Do the dipoles cancel out? Okay, so do they oppose each other? Think of it like a tug of war. If I'm pulling with, say, 1,000 newtons of force, and someone else is pulling in the opposite direction with 1,000 newtons of force, we cancel each other out. There's no movement. There's no net force. Same idea with these dipoles. If they both pull in opposite directions and are the same dipole, then they cancel each other out and we have a non-polar molecule. Alright? So my two options here again are yes or no. Okay? So if they do cancel out, that's the example I just described there. 1,000 newtons each way. If it was a tug of war, no net force, so therefore it's non-polar. And a really good example of this is carbon dioxide. Okay, a really good example. The CO bond is polar. The dipole is in the direction of the oxygen atoms because they have the higher electronegativity. So if I draw the Lewis structure for this, it actually shows us. And you can see that that's linear, which is a symmetrical shape. So this dipole is in this direction, this one's in this direction, just as strong. So they cancel each other out. Yes, there are polar bonds inside the molecule, but the molecule itself is non-polar. Another good example that's often given is tetrachloromethane, CCl4. It's a really common example given in assessments. Now, the reason I mention that is because I'm going to use dichloromethane to show you what happens when they don't cancel out. Okay, so they don't cancel out, it is polar. And as I say, the example I'm going to use here is CH2Cl2, which I think we've done in a previous piece of work. So we should know the Lewis structure, and I'm actually going to draw it this way on purpose, so it looks like they cancel out. Okay, if we just did the Lewis structure, it looks like the two polar bonds pull against each other and they cancel out. But if I draw it in 3 dimensions, it doesn't do that anymore. I can see that the chlorines are not one above the other. One's going slightly into the board and one's going straight up. So that's creating a net pull. One is pulling straight up, one is pulling back this way. So the net force of that is going to be that way. So you have a dipole in there in the direction of the chlorines. A net dipole creating a delta negative side of that molecule. Which means the hydrogen side of the molecule, the bit coming out of the board, that's the delta positive side of the molecule. Alright? So this little flow chart, if you can get this sort of in your mind, this little flow chart should really help you determine polarity really quickly. And with the exception of the very first step, where there are a couple of exceptions in year 13, it'll hold you in good stead for this year and next year. So it's more than just 1 year of use. Alright? You just have to know the couple of exceptions to that rule in year 13, and then it works really well. Okay, stop there.